And I can totally do that. I'm just wondering the best way to do this. Yeah, I can go. So I guess the thing we want to think about, or the thing that's important to think about, is the array. I'm just going to write the array because I might actually flip to another screen in a second. So we've got an array that has 52, 3, 7, 13. Oh. And we want to know the number of iterations, or the number of swaps during the first iteration of bubble sort, the number of iterations of the outside loop that will occur. And then for elements 7 through 9, how many comparisons there will be for insertion sort. So I guess to do this, let's go over and actually look at those algorithms really quick. So we've got this array for bubble sort. And again, I'm asking, I guess, how many comparisons will we make? So again, for the number of comparisons, what's going to happen is we are starting oh, this should be a J, but we're starting at the first one. We're saying how many times do I need to compare 52 with something else to have it bubble up? So it's going to compare it with 3, then it's going to swap. Then it's compare it with 7, it's going to swap. It's going to compare it with 13, it's going to swap. 21 swap, 23 swap, 37 swap, and 49 swap. So there's going to be 1, 2, 3, 4, 5, 6, 7 different comparisons, right? Because it's going to keep swapping, it's going to keep bubbling the 52 up all the way to the end of the array. So at the end of that, our array is, after it makes all those swaps, so it's going to swap 52 and 3. Then it's going to swap 52 and 7. So it's going to, again, keep swapping 52 and 7. Then it's going to swap 52 and 13, then 52 and 21, then 52 and 23, then 52 and 37, then 52 and 49, and then 52 will be at the end. So after the first iteration, so that's after so there was a swap, so it's true. So it's going to say repeat until swap is false. So then we're going to iterate this whole thing again. We're going to say, let's start swap at false. Let's start at index 0. And let's say if any are out of order, let's swap them. So in this next case, when it checks, are any of these out of order, it's going to find that none of them are out of order in the second iteration. So it'll never set swap to true. So the repeat until will break out. So after the second iteration, it's going to break out, and this bubble sort is going to be finished. So the first time it's going to have to make a lot of swaps, 1, 2, 3, 4, 5, 6, 7. But it only requires 2 iterations. Does that make sense? Because in the second iteration, we never have to make a swap, so the bubble sort algorithm finishes. Cool. So for the last question, for insertion sort, so for insertion sort, what did we ask? We asked, yeah, how many comparisons do each of these need to make? So what's going to happen is insertion sort is going to grab the first element and it's going to say, okay, I'm going to insert 52. I can insert 52 there because it's the only element I've sorted at this point. Then when it grabs the 3, it's going to say, okay, I need to shuffle 3 in front of 52. So then we're going to have a list that's 3 and 52. And then when it tries to sort 7, it's going to say, okay, I need to sort 7. I need to swap it before 52. Then I'm going to compare it with 3 because it's going to say, well, this value, well, A at index j is greater than my value. So it is greater than 52, or 52 is greater than 7, A of j, but 3 is not. So it's going to have to compare it with 3 and 52 to realize, okay, I found where I want to put it in. So it's going to put it in 3, 7, 52. Then when we have 13, 13 is going to say, okay, as long as this value is greater, it is. So I'm going to look at the next one. Oh, that broke. So I know I'm going to put it into here. So for each of these values, it's always going to compare it with 52 and continue looping. So it's going to loop through at least once, but the second loop is going to fail and it's going to know to put it. So it only has to shuffle over one spot. So the number of times it shuffles is always going to make one more comparison than the number of shuffles, because this condition eventually has to evaluate to false. So although each of the elements 7, 13, 21, 23, etc., all those elements only are going to shuffle over one spot. They're only going to have to shuffle over 52, to the left of 52. They are all going to make 2 comparisons in the loop. Like the loop is going to evaluate true the first time, and then the second comparison is going to break out of the while loop. So each one of them is going to have 2 comparisons. Does that make sense? No, it was how many does each one have? So each one's going to have 2 comparisons. I guess what I was trying to show here is that, again, if you think about this as being like these as being kind of nested loops, which we'll talk about today, you might think that they're always just going to be n squared because we've got a loop that could go kind of almost n times, a loop that could go almost n times. But what I was trying to illustrate with this is that in certain cases, when things are nearly sorted, they're actually much shorter. Any other questions? I will talk about that today. Oh yeah, so I guess before we do go into our discussion of this, I've been trying to write up something for our exam. So again, as we know, the exam is going to be on Connect. So I wanted to post something when I post some of the exam details after lecture today. And I've gone through all the exercises we've done this semester and tried to think about the ways that, again, using kind of a nice tool where we can actually write mathematical expressions, they kind of look like they do in this category. In the second column here. I mean, in a perfect world, or if exam was written on paper, we could write all of our things using these, all these like nice symbols and summations and easily write exponents and fractions and whatnot. But I was trying to think again, just with the plain text that is available in the test and quizzes tool, a way to I guess provide you with some general guidelines on how you can write these things. And I mean, this is what I've got so far. And if there's other things that come to mind, let me know, and I can update this. But I'll certainly have this, and I'll post this today, and also again remind you before the midterm. But again, the things I could think of as being issues is, again, if you've got something like this where you've got a number of terms on the top of a fraction, just make sure you're putting parentheses about to clearly denote what's part of the denominator and I guess what are the terms on each side of the fraction? Because without these red parentheses here, we might just think that the fraction is only, so again, if I removed this parenthesis here, it might seem like it's only, this is, the fraction is only considering these terms, and then I'm adding n to the result of that fraction. So again, for fractions, the main thing I think of is just making sure you add parentheses around your fractions. At this point, we're not going to do that. We're just going to use the tool. And again, similar for if you've got multiple terms in an exponent, whether it's the base or the exponent. Again, if the exponent here, just put fractions around it. If the base has multiple terms, put fractions around the base. Oh yeah, I'll add that greater than less than two symbols. Yeah, I think for this, what I'd say, and I'll add this as another row, is just for, as opposed to less than or equal to, just do it as this, and for greater than or equal to, just do greater than or equal to. Let's see. Yeah, so I mean, what you could do for the big O stuff is, yeah, just say like big O of n, big omega of n, stuff like that. So just actually write in big omega, big O, big omega, big theta. I mean, for big O, I mean, you could even just put an O. That's fine. Yeah. Anything else, people? So yeah, I'll make a note to write the greater than, less than, and add this to the document. But I think this kind of has most of it. And again, I'm going to try and avoid making you have to do a lot of this stuff. Again, with kind of doing kind of some multiple choice and other stuff like that. But I essentially just went through all the worksheets we've done and tried to look at kind of all the different types of things that showed up in the answers, and tried to add it to this table. And yeah, Dave, so uploading a PDF is something we could explore. I haven't set up the exam to do that this time, but that's something I can think about for the next midterm. I'll explore that as a possibility. But yeah, just the way that I've created the questions for this exam, I think the format and how I've got the grading set up, I think I've got it all set up to use the actual test and quizzes tool. This test will be 45 minutes, but yeah, I will. So after class, what I'll do is, I'll mention, I'll have a Connects announcement that'll email you everyone. It'll have this sheet that we were just looking at. It'll have the topics covered. It'll have the time. It'll have a reminder that assignment solutions are posted. Your assignments are both graded. I'll release those right after class. I didn't want to release them right before class, just because I want people to kind of be focusing on the lecture. I do have office hours right after lecture as well, so you'll have all your assignment stuff. You'll have all the solutions to the worksheets, and I'll release some exam details as well. yeah, so the material is up to and including asymptotic analysis, which is unit 5, but none of the Java ADT sorting stuff. So in my other exam, I was on Zoom the whole time. And some people, again, use Zoom to private message me if something came up. So yeah, that's what it worked. And I did get some minor questions. I guess Zoom is nice for if something happens with connects or something along that lines, then at least I can make an announcement that way and speak to you all immediately. So yeah, certainly almost the whole class was in the Zoom meeting when the midterm started. But after kind of a few minutes, as people kind of got into things, some people just closed the Zoom. But again, I think kind of throughout 115, I think there's probably about 40 people in the Zoom call the whole time. You will still have labs next week. Any other questions? Okay, so I will make an announcement that hopefully clarifies all these things, and I'll add Andy's suggestion to the, I guess, kind of exam guidelines sheet. And feel free to let me know if you have any other things. I can add it and update it over the weekend and send another email later. Okay. So why don't we jump to the sorting worksheet today. And again, although it is a new topic that's not testable, I do think some of the things we're going to be talking about today when we're talking about runtime analysis and stuff like that is obviously good to practice for the midterm, because there is going to be some runtime analysis is one of the topics that's covered on that exam. So hopefully in some ways, again, just looking at algorithms, looking at pseudocode, thinking about runtime analysis is just generally good practice for that examinable material. I'm just going to move my tablet over top here. So again, for these algorithms, we're first going to talk about kind of best case, average case, worst case runtime. And then we're also going to talk about stability in memory. So stability is where we think about if we're given this input array that again has some items in who knows what order, but if we have two items with the same key, so again, if it's an array of integers, they'd just be the same number. But again, it could be I don't know, data about where each person has a unique SIN number or student number, and people can be in that input collection in multiple ways, or we can have the same key. Are we still, once we finish sorting, are the people that were originally with the same key in the same order in the output array as they were in the input array? And I guess the stability kind of comes up more when we're talking about, I guess, priority-based ordering, where again, if I don't know, this is probably not a realistic example, but if in a hospital we've got this ordering of people that need to be helped in a different order, and again, if you're in like critical condition, you kind of get priority and get to go to the front of the line. If you're in I guess if you're kind of in moderate condition, then you're kind of middle priority, and then if it's not an emergency, or it's just a checkup or something like that, then maybe you're low priority or something like that. So you've got like really high priority, medium priority, and low priority. And I guess the idea here is that every time new people enter this waiting queue, we want to kind of sort it so the top priority people get to the front. And I guess the idea here is if there's someone that's in critical condition, a high priority person that's first in line and should be about to be helped, and someone that's also a high priority, but this person that's been waiting for an hour already, and this new person, same party, comes in, they don't actually skip them in line. So they get to move past all the low priority people, but they shouldn't actually, when we resort, jump ahead of the other people with the same priority or same key in terms of the ordering. So stability can be important, and it's something that once we look at different sorting algorithms, we'll see that it's not something to necessarily take for granted, because some sorting algorithms can't maintain this property. the last thing is memory. And again, we'll see, again, these are just our first 3 sorting algorithms. We're going to explore a number of sorting algorithms over the next few weeks that again, some are extremely fast, but require a lot of additional memory. Whereas, again, some don't require any additional memory at all. So again, these are things that at this point, and for these particular sorting algorithms we're looking at today, there isn't anything too interesting with respect to stability or memory usage, but they do become factors in some of the later sorting algorithms we think about. Does that kind of make sense? Cool. Okay, so why don't we just start at selection sort? And I think, I guess depending on when you took 110 and or 111, it may be something you've seen before. It is, I think, kind of traditionally one of the first, probably this and bubble sort are often the first sorting algorithms that are introduced. And again, the idea is you've got an outer for loop that is going to always search for the smallest value and swap it to the first unsorted section of the array. So we saw that animation in the video where it searched all the way through, grabbed the smallest element, swapped it to the front. Searched all the way through, grabbed the element, swapped it to the front. One thing you might have noticed about selection sort is that even if the array was perfectly sorted already, it's still going to say, okay, let's say that this is the minimum value, and it actually is the minimum value. But it's still going to search through all the other values here and say, hey, is this value smaller than the min? Is this value smaller than the min? Is this value? And it's going to still it's still going to search through all the other values up to the last one and determine whether it is smaller before trying to make that swap. So even if the array is already sorted, it's still going to have to do the same number of comparisons, same number of operations. I guess the one optimization you can do is you can say if min never changed, then don't swap it. But other than that, you're still going to have to do the same number of comparisons. And maybe I should say that for today, the main way, and this is kind of traditionally how sorting algorithms are compared with one another, is let's simply focus on counting comparisons. So for selection sort, no matter if it's perfectly sorted, if it's complete opposite order, or whatever it is, it's still going to make the exact same number of these, because every loop, it's always going to go from 0 to n minus up to and including n minus 2. It's always going to start at I plus 1 because we're grabbing the first value as I here. And it's always going to compare that number with all of the other n minus 1 values after it and see if any of them are smaller than it. So again, in the first iteration, if we've got some so again, and let's I purposely have a duplicate entry here. So again, we're going to say let's start our min as 4. And let's going to see if this number is smaller than min, or this number, and this number, and this number. And we're going to look through all the other items and see how to get that minimum number. And then we're going to swap it to this first index. Then we're going to do the same thing. We're going to say this is the min and look at all the remaining items. So again, it's always looking at all the remaining items. So if we think about the number of comparisons here, the first iteration n minus 1 comparisons. So it compares this 4 with all n minus 1 other values in the array. Then we swap, what we'll do is we'll swap the 1 to the front, and then we'll have to make, during the second iteration, min will start out as the second value, and we'll compare with all n minus 2 values to the right of it. So first iteration makes n minus 1 comparisons. Second iteration makes n minus 2. And what we'll see is the third iteration makes n minus 3. down to only a single comparison at the end. So again, what we've got is we've got 1 plus 2 plus 3 plus comparisons. If we think about how many times in total, how many comparisons we're going to do over the whole algorithm. So I kind of showed this off before a couple slides ago, but this is again just that summation where we can think about this as we've got, if we think about these as pairs, we've got n minus 1 over 2 pairs that sum to n minus 1 plus 1 is n minus 2 plus 2 is n. So therefore, this is n times n minus 1 over 2, which is n squared. And it's always going to be n squared. So it's important to note that no matter how the input array is arranged, so I'm just saying that we've got, if we add up the first and the last term, those sum to n. If we add up the second term and the second last term, those add to n. The third term and the third last term, those add to n. So we've got n minus what we've got. If we think about the number of pairs, it's this the input size divided by 2 because I'm pairing them all up. So we've got n minus 1 over 2 pairs and all of them sum to n. Yeah. So for this one, all 3 cases are actually the same. But what do we think for stability? Do we think that we can make this algorithm so if things start in the same order, they will end up in the same order? What do people think about that? So I think so. I mean, my initial guess, oh yeah, sorry. I don't know where, yeah, this is n minus 1 pairs. I don't know, I just didn't write it over there. Yeah, n minus 1 over 2 pairs of n, yeah. Yeah, so it seems like it should, but let's think about this for a second. So I'm gonna erase what I've got over here. So again, we started with this array here, and what we know is gonna happen is it's gonna search through the whole array, and it's gonna find the smallest element, which is here, and it's gonna swap this with the 4. And so what's gonna happen is our next array is gonna be 1, 2, 7, 4, 1, 4, 6, 3. And we know that this is now, again, this is now sorted. This is our sorted section. So now it's going to search for the next smallest number from here onward. Right? But the problem is, what we've done now is, if we think about it, this 4 used to come first and this 4 used to come second, right? But now the one that came second is ahead of the one that came first. And the thing is, when we do these swaps, we lose track of which one was originally first and which one was originally second. So we can't ever guarantee that 2 items with the same key are eventually going to end up getting the position. Because we, again, even if we, depending on how we when we search for a minimum, how we handle ties, that doesn't matter because we don't know in which order these are going to get swapped to the back end. That's the main issue, is when we're trying to find when we see a tie, we can't just say, let's keep the one that's the leftmost when I see a tie, because that one might not have been originally the leftmost because it might have been swapped behind it. And again, we might make another swap again. So it's impossible to keep track of which one was originally came first if we're doing these swaps back into random spots. So I'm going to say no, we can't determine which originally came first after our swaps occur. Yeah, n is the size of the array. Up here it says that. Or n is the number of elements we're working with. It's the input size. Yeah, I guess it doesn't necessarily have to have a full array, but that's the number of elements. Yeah. And in terms of memory, we're actually going to, for memory, we often also write memory the same way we write our runtime analysis. So again, we can say that all these are O of n squared. Stability means that if we've got two items that have the same key, whatever we're choosing to set the ordering of our elements, that if two things are in this, if one comes before each other in the input array, after we finish sorting, they still will come in this, they will still be ordered in the same fashion. So if we have two ties here, when we're trying to sort this number, this array up at the top, this first four, when it's sorted, if it was stable, we want to be able to guarantee that at the end, this first four still comes before the second four, but we can't do that. So when there's a tie, we want to make sure that the way that the items that have the tie were ordered in to begin with, after we finish the sorting, they're still in that same order. So for the memory, we often write this in big O as well. And what I'm going to say is this is constant, because what I mean by that is that there's no extra memory, or I guess auxiliary memory, I should say. But yeah, no extra memory required So again, we're always, I guess the only thing we're really using is a couple of variables. Like we're declaring an I variable, maybe a min variable, and we're maybe a temp variable in the swap. But that's the only three variables we're creating. Maybe a temp variable here, a min variable here, a j variable here, and an I variable here. So 4 variables are probably what we're creating. But we're always creating those 4 variables. It doesn't matter if the input size is 1,000 or 1,000,000. We're always, the additional things that we're creating to make this algorithm go is constant. It's always just going to be these same 4 variables. The memory here is what additional structures do we need to allocate in memory as our input size increases? And we don't. We always need to allocate just 4 temporary variables. Yeah. But what we're going to see is for some sorting algorithms, it's going to make us allocate a whole new temporary array. And so if we had to do that and our input size is 1,000,000, we're going to need to allocate another 1,000,000 size array to do that. So in that case, that would be bad. The memory the memory requirements would grow at the same rate as the input size. So that obviously isn't great from a memory perspective. But this one doesn't. Again, we're just making a couple of temporary integers. And again, it doesn't matter if there's 5 elements in the array or 1,000,000. We don't have to, the amount of memory we need to allocate to, in addition to what we're given, isn't going to be very much. So I guess in addition to what the parameters are, how much extra memory do we have to allocate as our input size increases? So that's what this, I guess, a extra or auxiliary or additional memory is what we're thinking about here. Any other questions? Okay, I'm going to clear this then because I think I'll scroll down and do the bubble sort. So for bubble sort, yeah, we're always going to allocate our loop variables a min and a temp when we swap. But again, we're not going to have to allocate more variables. Like, it's not like when our input array is size 10, we have to allocate 4 variables. And when it's a million, we have to allocate 4 million variables. We're always allocating the same 4 variables, no matter how big our input array is. Yeah. So it's always constant. The number of variables we have to allocate is constant. It's always the same number. It doesn't get worse with our input size. Is really what we're trying to denote with that. Okay, so for bubble sort, we kind of saw almost a bubble sort, the best case scenario in the pre-lecture quiz. So if we have an array like this, where we've got 7, 9, 11, 20, 35, 51, again, what we're going to do is we're going to come into this first loop. We're going to say swap is false. We're going to say, okay, if any of these are out of order, I'm going to swap. But none of them are out of order. So in the best case, we actually have to make all these, we have to make n-1 comparisons. But then we see, oh, swapped is still false. I never had to make a single swap, so I'm done. So the best case here is when the input array is sorted. And in this case, we make n-1 comparisons in the first iteration. And then the algorithm ends. So I guess one of the nice things about bubble sort is that it is an algorithm where it can detect when if the array happens to be sorted early, and it finishes. It doesn't waste any cases. Whereas in selection sort, even if our input array was already perfectly sorted, it would still go through n squared times. This should be, there's a typo in my thing. These should all be I's or J's. Yeah. So we're just going through and we're comparing all of the adjacent items, and we're only setting swap to true if we actually have to make a swap. But if they're all in the right order, we don't make any swaps. So in this case, our total number of comparisons is just n-1. Which is big O of n. So our best case here we see is better than our selection sort. It just has to make the original n-1 comparisons, but then it's done. in the worst case, that would be when the input array is, I guess, in reverse order. So if we think about that, we're going to need to make the 9 bubble up, bubble up, bubble up, bubble up, bubble up, bubble up. So it's going to have to actually swap with the 8, then swap with the 7, then swap with the 6, then swap with the 5, then swap with the 4, then swap with the 3. So after our first iteration, all we've got is we've got the 9 in the right location, which is great. But then then with the 8, I still need to make 8 go bubble up, bubble up, bubble up, bubble up, bubble up. So again, in the worst case, we're doing n-1 comparisons, then n-2 comparisons, because we don't have to do the last one. And then n-3 comparisons, et cetera, et cetera. So in this, we do first iteration, n-1 comparisons, second iteration, et cetera, down to the last one. When we've just got 4 and 3 at the front, then we just need to make the 1 swap. So what we might see is that this is the same number of comparisons as selection sort. So in the worst case, bubble sort and selection sort make the same number of comparisons. It's again 1 plus 2 plus 3 all the way up to n-1, which again, I wrote it one way. We can also think of this as the which is n squared. Oops. Because we have to do a whole bunch of bubbling. We have to bubble up, yeah, the first one, n-1, then n-2, then n-3, then n-4, et cetera, et cetera. Does that make sense? So then the average case, again, is it closer? What do we think? Is it closer to the best or the worst case? Somewhere in the middle. So there are a number of different ways we can do this, and we can calculate all the different permutations that could happen from best case to worst case and get the average that way. So again, we could calculate all permutations and average. But yeah, I think one thing, what we might do is, again, we know that we have to do 1 plus 2 plus 3 plus 4 plus 5. In the worst case, we had to do again, n minus 1 comparisons and n minus 2 comparisons, all the way down here. And let's just say that if we get rid of, let's say that every kind of second value in the array is maybe sorted, so we don't have to make any comparisons. It's already, we realize at that case that it's great. So we'll get rid of half of these terms. So now what we've got here is really, we've now got, we're again dividing the number of pairs that sum to n by 2. So before we had n minus 1 over 2 pairs that sum to n. Now we can just divide that by 2 to have n minus 1 over 4 pairs that sum to n. So even if we do this, we'll see that, again, this is still going to be O of n squared. And again, even if we did this even further and said, oh, let's make this divided by 8 or divided by 16, that would still be n squared. Because it's still just some constant number. So again, even if we have far, even if we're, again, not even in the middle in terms of kind of having half of them be really bad and half of them be good, we're still going to be O of n squared there. I guess another way I could have written this is just, we had originally n minus 1 squared, and if we again just said, let's just divide this whole thing by 2, get rid of half of those pairs. I can rewrite that. So we had n of n minus 1 over 2, and then we said, let's just divide this whole thing by 2, which is going to get us n of n minus 1 over 4, which is still going to be O of n squared. So we have a couple minutes left. What do we think for stability in memory? Yeah, so I guess so I'm seeing no stability and stable. So again, I think it depends on what we do here in this if check. So again, we always want to make sure that if we see another 8, so like let's say there's another 8 in here somewhere. We want to make sure, or sorry, another 9. But when we're making our comparisons, when we're saying, is it bigger, is it bigger, is it bigger? We're not going to swap. We're going to make sure that we don't swap this first 9 onto past that second 9. So we make sure that when we make this comparison, we say, oh no, I'm only going to swap it if it's clearly bigger, not if it's less than or equal to. So at that point, then we'd start putting this other 9 back to the end. So yeah, depending on how we implement it, if we're careful with our comparison here, yeah, it depends on an if statement, but it is possible to ensure that it is stable. Yeah, exactly, Kevin. It's stable, assuming that we say we're only going to swap if it's strictly greater than. And for memory, again, we might have to, we're allocating a few kind of temporary variables, but again, we're always going to allocate the same number of variables. We've got a Boolean, we've got a J, and maybe a temporary variable for our swap. We're always just going to allocate those same 3 variables. It doesn't matter if our input size has 1,000,000 elements or just 10. Does that make sense? So what we'll see, again, we're going to jump into some other sorting algorithms after the midterm. But what we'll see is, again, as I said, for stability and memory, there wasn't anything too interesting here. But we'll see for some of our later sorting algorithms, they're going to have better best case and or sometimes better best case and worst case running times. But sometimes we'd still might use something like bubble sort if we know that we're near the best case and stability and memory are actually important to us. So there are certain situations, even though it's got a really bad worst case, n squared is something that we're going to look up a bunch of other sorting algorithms that work, it still could be a choice if we know that our input size is small and stability and memory are of utmost importance to us. So yeah, what I'll do within the next few minutes, I have office hours at 10:30, but between now and office hours, I'll release the assignment grades. The assignment solution is already posted, and I can write a quick message, just announcement, just with the document that I showed off at the start of class and some details about the midterm. I will also have some additional office hours that I'll announce, both tomorrow and Sunday. So there's office hours today, Saturday, Sunday, and Monday. So all 4 days leading up to the exam. I think at this point, I'll probably do Saturday morning and then Sunday afternoon to try to get one in the morning, one in the afternoon, just in case people have different work schedules on the weekend. Hopefully someone, I mean, if you want to come in and ask questions at office hours, hopefully one of the times will work for everyone. And I think that's about it. So again, during lecture on Tuesday, our next lecture, during our lecture, I will still have the Zoom call, but the exam will take place during that lecture. So at 9:30 a.m. on Tuesday. Any questions before we wrap it up here? No problem. Yeah. So the deletion one, Leo. I'm not talking about I'm not sure the selection sort. Yeah, so maybe on Wednesday, I'll do videos for the new sorting algorithms, and then we will cover insertion and then talk about, go through a few other of the sorting algorithms. Yeah, so we'll do insertion on Wednesday. Okay, I'll stop the recording, and I can answer any questions as well for a couple minutes, and then I'm going to hop over to office hours shortly.